We're picking up here in the middle of section 9.6. We're talking about quantum mechanical orbitals. The quantum mechanic model of the atom is not the solar system model, the Bohr model, because that actually turned out to be not correct. And so this is the currently accepted model of the atom. So there are different shells or principal energy levels. I'm actually going to go off into one of my silly analogies, and we're going to think about a hotel. This hotel is in Las Vegas. You ever been to Las Vegas? There's some pretty interesting architecture, right? There's that one casino that's like this pyramid and it's all mirrored and everything. There's just some really odd-looking architecture. So that's why my hotel here is in Las Vegas, because this is like an inverted pyramid kind of structure. Now that would not be good, like in San Francisco, because you get a little earthquake and that thing's just going to fall right over. But whatever. So here's my strange hotel. Each of these boxes represents a room in the hotel. Hotels have lots of rooms, right? And so these levels are different floors. So shell number 1 is the first floor in the hotel. On the first floor, there's only one room. And for whatever strange Las Vegas reason, it's not room number 1, it's room S. On the second floor, there are 2 rooms. Room S and room P. Again, don't ask me about the letters. It's crazy. Third floor, 3 rooms. Fourth floor, 4 rooms. How many rooms do you think there would be on the 5th floor? 5. There's a pattern here, right? The number of rooms is equal to the floor number. Okay? So, what does this correspond to with electrons? Well, each of these boxes is a subshell. Think of it as a room for electrons to be in. Now, you go to Las Vegas, and do you spend all your time in the hotel room? No. Now, maybe newlyweds would spend more time in there, but still, the reason you go to Las Vegas is not only the hotel room. So there's a probability that the electrons are in the room. I think of the electrons as people. And so this S room, 2 electrons can stay in that room. They're not always in the room, though. They could be outside, but this is where they're hanging out. On the second floor, there are 2 different rooms that the electrons can be in. So an orbital is a place where an electron can be. These subshells are a group of orbitals, because actually the orbital itself is the bed in the room. And people sleep in the beds, electrons sleep in the orbitals. So the S subshell has 1 orbital. So there's one bed. There's one bed in that room. Sometimes this analogy goes better than other times. So all the S rooms have 1 bed. The P rooms have 3 beds. I told you this was a strange hotel. The D room has 5 beds. And the F room has 7. There's a pattern here as well. So the first floor has 1 room. In the 1 room is 1 bed. How many people can sleep in 1 bed? 2 people. Okay. So every bed is an orbital. An orbital can hold 2 electrons. The second level, the second floor, has 2 rooms. The S room has 1 bed. The P room, like they have the double room and the queen room and the suite, and they have different numbers of beds, right? So this is the P room, has 3 beds. On the 3rd floor, you've got an S room, a P room, and a D room. The D room has 5 beds. So how many people could stay in the D room? 10. Because each bed could hold 2 people, right? They don't allow people sleeping on the floor. And in the P room, how many people? 6. And in the S room? 2. Okay. The other thing about this hotel is the higher you go, the better your view out the window, right? And so you're going to pay more money to stay in a room on a higher floor. With the electrons, n equals 1, this is the level where electrons have the lowest energy. N equals 2, the second floor in the hotel, is more energy. And 3 is more, and 4 is more, and 5, and it just goes up. Does that make sense? So you're paying more money to stay on a higher floor of the hotel, and if you need a reason, it's because you have a better view. And as we go up, there are more and more rooms. There's also a difference in cost between the S room, the P room, and the D room. That gets a little bit complicated, but I kind of think of it as the elevator goes up and down over here, and so the S room is noisier because it's closer to the elevator. There's people walking by all the time. And as you get farther and farther from the elevator, the rooms get a little more expensive because they're quieter. So with the electrons and quantum mechanics, the shell number, you can think of that as roughly being like the orbits in that solar system model. N equals 2, the second level, is farther from the nucleus. In my hotel, the nucleus is the front desk. And so on the second level, it's farther from the front desk. And the third level is even farther, and the fourth is farther. S and P rooms are right next to each other on the second floor, so they're very similar in distance from the front desk. The S and P orbitals in shell 2, principal level 2, are similar in distance from the nucleus. I don't remember what slide's next. So this kind of goes over some things I've already said. The third principal shell has 3 subshells, S, P, D, S, P, and D. So the third floor of the hotel has 3 rooms. Third floor, 3 rooms, S, P, and D. The S and P subshells, the rooms have 3s and 3p orbitals. So remember we looked at these funky shapes. The s orbitals aren't too bad. They're spherical. And this one is the one in the lower level. It's closer to the nucleus. The one on the second level is a little farther from the nucleus. Electrons that are in this second s orbital are higher in energy than ones in the 1s orbital. And so this orbital is called the 1s because it's on the first level and it's the s room. This one's the 2s because it's on the second level, the s room. And here are pictures of the orbitals. The second floor, the second level, is the first one that has a P room. There is no P room on the first floor of the hotel. There are no P orbitals on the first level in the atom. So there are 3 different orbitals. Remember I said each of these is like a bed that can hold 2 electrons. So we could have 6 electrons. There'd be 2 in this one, and 2 in this one, and 2 in this one. But all of these together have the same energy. You've got a hotel room with 3 beds. Can the hotel specify, well, if you're going to sleep in this bed, it's going to cost you more money than if you sleep in that bed? They can't do that. They charge each person the same to stay in the same room. So in this subshell, where there are 3 orbitals, beds for electrons, each of those orbitals has the same amount of energy. The electrons would pay the same amount of money regardless of which of these beds they're going to sleep in that P room. Is this making any sense? It's very weird. I'll give you that. You go to the D subshell, the D room, that has 5 D orbitals. That has 5 electron beds. This is what the D orbitals look like. You thought the P's were strange. I'm not going to test you on this. I'm not even going to waste breath talking about it. They're weird. Okay. So we're talking about these orbitals, these electron beds. How are they occupied by electrons? Well, we've come up with a shorthand, a couple of different shorthands actually, to specify where the electrons are in this mass of different orbitals. And this is a little bit like a shorthand that the front desk clerk might use to keep track of what guests are in which rooms. Because when another guest comes, you don't want to send him to a room that's already occupied, right? So this is called an electron configuration. It's just a shorthand to tell us what orbitals, what electron beds are occupied. So in the hydrogen atom, there's only 1 electron. So electrons are budget conscious, okay? So they go to this hotel and they're not going to stay in the penthouse because they're not rich. They're just ordinary people. They're happy to be here, but they're going to take the cheapest room they can get. So if there's only 1 electron staying in the hotel, he's going to stay in the lowest energy orbital, the cheapest room. That's the one on the ground floor closest to the elevator. That's the first floor, the S room. The first energy level, the S orbital. There's only the 1 orbital on that first floor. And so we indicate his presence here. There's the floor number, the room letter, and this superscript is how many electrons are there. So for hydrogen, it's just 1s with a superscript 1. Electron configurations are one place where chemists do write the number 1. Another way we can do this is by drawing little pictures. These are called orbital diagrams. Diagrams suggest you're drawing a picture. And here we make a little box for each of the orbitals. So the hotel clerk has a little box for each bed, and he groups them. Here's the 3 beds in that room and the 5 beds in this room, and then little arrows to indicate that the electrons are staying in that particular bed or that particular orbital. So this is the 1s orbital represented by a box. By convention, we draw an arrow with only half of a head. It's not a double-headed arrow pointing up. And this represents that there's 1 electron. So it's a little bit like you're drawing pictures. It's so funny to look at your expressions. You're very concerned. What on earth are you talking about? So, he got tired of drawing little stick people, and so he just draws an arrow. But here I'm drawing the bed, and there's 1 person staying there. Okay, that's what an orbital diagram is doing. Electrons have a property called spin. And in a very simplistic way, you could think of them spinning like tops, and one spinning clockwise and the other spinning counterclockwise. Very simplistic, but it gets the idea across. To put 2 electrons in the same orbital, their spins have to be opposite. Otherwise, they do not get along. So electron spin in my chemistry land, strange Vegas-style hotel corresponds to gender. So in this hotel, if you're going to have 2 people in a bed, you have to have 1 guy and 1 girl. I don't know why. It's just what they decided. No comments on any actual people or anything intended. So there's a concept called the Pauli exclusion principle, And that says that orbitals may hold no more than 2 electrons with opposing spins. And we symbolize these as 2 arrows pointing in opposite directions. So if I'm going to draw a picture, an orbital diagram, let's say this is the 1s orbital, and I'm going to indicate that there's 2 electrons in there. I'm going to have one pointing up and one pointing down. And so, that's a little bit equivalent to the hotel clerk saying, okay, there's a guy and there's the girl, right? Or we have gender symbols, right? I can never remember which one's which. Well, actually I can, but I don't have to go into that, why I remember. Anyway, you need one of each if they're going to be together. You can't put 2 up arrows together or 2 down arrows together. Okay, so let's just kind of jump in here. We're going to write electron configurations and orbital diagrams for helium and for lithium. I find the orbital diagrams to be a little easier to start with. So we'll do the orbital diagram first, and then we'll do the electron configuration. So, helium. First of all, we need to know how many electrons does helium have? 2. It's element number 2 in the periodic table. It has 2 electrons. So we've got 2 electrons. So then I'm going to think about the crazy electron hotel. And I'm going to draw a box representing the bed in the first room. How do we designate that cheapest room in the hotel? 1S. It's on the first floor because as you go up, the rooms get more expensive, right? So it's on the first floor, and the room closest to the elevator is called S. Just because. No great reason I can hand you there. 1S. So could we put 2 people in this room? We could. There's only 1 bed in there, but they could share a bed. And so we've got a guy and a girl. That is the orbital diagram for helium. And then electron configuration is using numbers and letters and superscripts as a shorthand. So we say, well, there's the 1s room, and how many electrons are in it? 2. So I'll have a superscript of 2. That tells me there are 2 electrons in the 1s subshell. A subshell is a room, an orbital is a bed. How about lithium? How many electrons does lithium have? 3. 3 electrons. So I'm the hotel manager. I've got these 3 electrons coming in. They're saying, we need beds. We want to stay here. But we don't want to spend a lot of money. So we say, well, I have this 1S room that has a bed. And so, we'll take it. Well, I can only put 2 of you in there. So we'll put a guy and a girl. And then where's the 3rd electron going to go? It's going to have to go up to the 2nd floor. Going to have to spend more money, be higher in energy. The first room on the 2nd floor is the 2s. And so we'll put 1 electron in there. We're going to fill the hotel up from the ground floor, and we'll go to the 2nd floor, and we'll move over. They're going to go into the rooms that are cheapest first. And so how would I designate in an electron configuration for this one? We've got 1s2, and then 2s, and there's 1 electron in that.
Do you write all of that, or do you just?
I do write all of this. Mm-hmm.
Okay.
Yeah.
It's not implied that because it has to be in full first, you don't just write the last one?
No, you would think that you could just do the last one and assume that everything else was full. And in this class, we could get away with that, but that's not what chemists do. And see, it is possible for one of these electrons to maybe win at the slot machines, get a lot of money, and decide they want to blow it on a better view and go up to a higher room temporarily. And so that's not going to be a stable thing. That's what's called an excited state. That's what happens when the energy comes in and electrons absorb energy. It's like they got this influx of money and they blow it by jumping up to an excited state. They jump up to a higher energy level. It's not stable. They won't stay up there. When they come back down, they lose that money. The energy comes back out, and that's where we saw the lines of color, was from the electrons going from that higher orbital back down to a lower energy orbital. So you can have an electron configuration for an excited state of an atom where there may be gaps in some of the lower parts. And so that's why we don't just put the last term. So any questions on this? Okay. So unfortunately, it's a little more complicated than that. It's a little bit like Groupon or something. There's these deals on these rooms. So again, this kind of looks like my crazy hotel. That's not what I wanted. Yellow's no good there. Red. All right, so here's my crazy hotel. Here's the first floor. This has one room, the S room with one bed. Second floor has an S room with one bed. This is the next room over. Now I'm indicating each of these beds as a line. We sometimes do this also. The third level, there's an S room with one bed, a P room with 3 beds. The D room has 5 beds. But the way we're drawing it this way, we're not drawing these on the same level like they were drawn before, because now we're looking at energy, or we could think of that as the price. So this is more of a price diagram. The 1S is cheapest, 2S is next, you go up, 2P, maybe seems strange, you have to pay more to be in this 2P room, 3S, 3P, this is all making okay sense, and then things get a little wonky. It's actually cheaper to stay in the 4S room than it is in the 3D room. I'm sorry, it's just how it is. There's like a deal or something, if that makes you feel any better. So this is showing us the price breakdown. This is cheapest, that's next, and then this, and this, and this. As we go up, this is more expensive, this is more expensive, that, and that. And so there's this crazy order here. 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S, 4D. And this starts to look like a big old jumble at the end, doesn't it? Like, what? Okay, just bear with me. I will show you how you can see all of this. It's all hiding in the periodic table. So that actually is a picture of where electrons are in my hotel, but it's disguised as the periodic table. I know, I'm being absolutely ridiculous. Let's write the electron configuration for carbon. We don't have to worry about the too much of that craziness yet. So it says electron configuration and orbital diagram. Again, I like the orbital diagram first at this point. Carbon has how many electrons? 6. 6 electrons. So the cheapest room is 1S. So we could put 2 electrons in there. And then next is that 2s room. And we could put 2 electrons in there. And what's the next room? The 2p. The 2p room has how many beds? 3 beds. The s has 1, the p has 3, the d has 5, the f has 7. So in my orbital diagram, I'm going to draw the 3 beds all together because they're in the same room. So this is the 2p room in my hotel. This is the 2p subshell. There are shells and subshells and orbitals, different organization levels. And when you say shell, subshell, and orbital, people's brains freak out. When you say floor, room, and bed, people understand that level of organization, right? So that's all that this is. So now, how many electrons do I still have to find places for? 2. Okay, so let's think about this. We're putting 2 electrons into this room that has 3 beds. What would people do? Would they both sleep in the same bed, or would they take their own bed? They'd probably take their own bed. And that's what electrons do. And so we'll put this electron in that bed and this electron in that bed. These electrons are weird because they can switch their gender. They can switch spin. You can draw them however you want. So the analogy breaks down after a little bit. That's a good question. Do I have to put them next to each other, or could I put this guy over here? Normally, we put them next to each other. So normally, we would fill them in order from left to right. And the Hund's rule says when you're filling orbitals of equal energy, these orbitals are equal energy. They're in the same room. You can't charge somebody more because they're going to sleep in a particular bed in the same room. Because they're going to claim that they're going to sleep in the cheap bed, and you're not going to be able to go in and check on them. When filling orbitals of equal energy, electrons fill them singly first with parallel spins. So we'll take these 3 orbitals and we'll put 1 electron in each of them with parallel spins. We always do up first. So up spin first, and then if we have to, we'll come back and pair them with an opposite spin. This is one method that people use to keep track of the filling order, the order or the price levels in the hotel. Is you can draw this, here's the first level has 1, the second level has 2, the third has 3, the fourth has 4, etc. And then the way you would figure this out is you draw diagonal lines. So this is the first one you come to, then you jump back up here, then you come to that one, that's 2s, right here 2s, then you jump back up, 2p, 3s, 2p, 3s, we jump back up here, 3p, 4s, 3p, 4s, jump up here, 3d, 4p, 5s, jump back up, 4d, 5p, 6s. So some students like this diagram. It makes sense to them. If it makes sense to you, great, use it. Otherwise, forget about it. So trying to summarize here, lower energy orbitals get filled before higher energy orbitals get filled. Electrons are cheap. They're going to take the less expensive rooms before they shell out extra money to go into a higher energy, higher cost room. Orbitals can hold no more than 2 electrons each. Beds can hold no more than 2 people each. When 2 electrons occupy the same orbital, they must have opposing spins. When 2 people occupy the same bed, they must have opposite genders. That's called the Pauli exclusion principle. When orbitals of identical energy are available, when beds of the same cost are available, all of them are first occupied singly by electrons with parallel spins, rather than electrons in pairs. You send 3 guys to sleep in a hotel room that has 3 beds. They're each going to take their own bed, right? They're not going to share, because guys don't share beds. They don't. They'd rather sleep on the floor. Okay, so let's look at larger atoms. Nitrogen. How many electrons does nitrogen have? Oh, you know what I forgot? Well, I don't think I can resume. I've gone too far. Anyway, I forgot to do the electron configuration for carbon. Oh, well. So, 7 electrons for nitrogen. Let's try to do it without the boxes. So the first room was 1s, right? The S room can hold how many? 2. So we'll fill that one up. And then the next room is the 2s. That can also hold 2. Right? And so now we've got 4 electrons settled. And then the next room is 2p. The p room can hold how many? It has 3 beds, so how many people? It can hold 6. So we can put the remaining 3 in here. 2 plus 2 plus 3 equals 7. The superscripts add up to the number of electrons that you're dealing with. So I like pictures. I like the orbital diagrams. So doing the orbital diagram, you go 1, 2, 3, 4, 5, 6, 7. Where would the 8th one go if there was an 8th one? It would go in here with the opposite spin. So let's look at oxygen. How many electrons does oxygen have? 8. So let's use this same orbital diagram here. We've got 7. The 8th one, I'll make it different color. The 8th one is going to go in there. So then the electron configuration for oxygen is going to be what? 1s2, 2s2, 2p4. It's oxygen. How about fluorine? How many electrons does fluorine have? 9. So that's going to be just like oxygen, but with 1 more electron. Where does that electron go? It goes in this middle box. I didn't do a very good job there. That's showing up okay. It's this guy right here. So there's a lot of repetition when we write these electron configurations. So this is 1s2, 2s2, 2p, 5. What about neon? It's 1 more electron. So that's going to fill up that last bed. So I'll stick neon down here. Neon has 10 electrons. One s2, 2s2, 2p6. Are there any more rooms on the second floor? No, there's only the 2. Neon is special because it completely fills the highest floor in a hotel that has any electrons in it. The first one's full, the second one is completely full. Fluorine, it wasn't quite full. There was still room for 1 more. Nitrogen wasn't completely full, but neon is special because it completely fills up everything. You think about, so OCD is a serious condition, and it's sort of unfortunate that people laugh about it and make jokes about it, and yet I think we can all kind of relate to that a little bit. And so neon would make an OCD person happy, right? Because all the boxes are full. Everything is just right. So all the noble gases actually do that, and that's why they are so stable and don't react with other things. Other elements, like fluorine, are trying to be like neon. They're like, we're not quite right. I need to fill up that other bed. I need more electrons to get in here, and so they react with other elements so that they can get their electrons all lined up just right. We do have an abbreviation that will save us from some of the 1s2, 2s2, 2p6 business that we have to write all the time. It's called a noble gas configuration, and it's a shorthand. So let's look at sodium. How many electrons does sodium have? 11. So sodium has, that's an A, that looks enough like an A, 11 electrons. I'm going to go ahead and draw those boxes again. So there's 1s, and there's 2s, and then there's 2p, and then we have to go up to the next floor, the next shell, and so there's going to be 3s, and then let's put the electrons in here. So I'm just going to count 1, 2, 3, 4, 5, 6, 7. Those electrons are going to spread out if they can. 8, 9, 10, 11. So the electron configuration then is 1s2, 2s2, 2p6, 3s1. In the 1s there are 2. 1s2. In the 2s there's 2. 2s2. In the 2p there are 6. 2p6. And in 3s there's only 1 electron. 3s1. Okay, so this part right here, how many electrons are represented in that part? 10 electrons. That's the same as the electron configuration for which element? For neon. Neon has 10 electrons. So this part here is equivalent to neon. So what we do is, instead of writing this part, we write neon in brackets. And so we say the electron configuration for neon, and then we just write this extra piece, 3s1. So these are two acceptable ways to indicate the electron configuration for sodium. This is obviously shorter, right? So, okay, well, it's neon plus 3s1. They always fill in the same order. Any questions? I kind of hate teaching this stuff because I feel like I'm dropping this psychological bomb on you or something and just like blowing your minds. Although it is a little fun too, but. Let's just do the first one. I really need to revise these slides. I mean, the book does a good job, but I'd rather come back and do these guys after we look at the periodic table. But let's do aluminum. How many electrons does aluminum have? 13. 13 electrons. So, writing an electron configuration, that's the 1s2 business. So we got 1s2, and what's next? 2s2, 2p6, 3s2, and then we might want to say to ourselves, well, let's see how many do we have accounted for here. So there's 2 and 2 is 4, and 6 is 10. We've got 12. We've got one more. What's the next one? 3p. So it'll be 3p1. You do have to put the 1. Normally in chemistry we don't put the 1, but in electron configurations I'm writing the 1 here, and I'm writing 1s as superscripts when needed. So that is very different from when we do chemical formulas. Yeah. So let's ignore bromine and strontium for now. Any questions? Yes? I could, yes. What would that be? So neon, and that represents this part. And then I write the stuff that comes after, 3s2, 3p1. It depends on the question. I think sometimes they'll make you do the whole thing. And because it's on the computer, they've got different, sometimes you just click to put arrows in places. And, so there's a variety of ways that they have you do it. And sometimes either is acceptable, and sometimes they only want the noble gas shorthand, and other times you want the full thing. You need to understand both of them. So writing these from scratch like this is actually a little harder than what you'll have to do on one of my exams, where if I'm saying, what's the electron configuration for aluminum, you'll be looking at 4 or 5 choices and picking the correct one. And I think that's generally a little easier than coming up with it from nothing. Any other questions? Let's do an orbital diagram for argon. How many electrons does argon have? 18. So let's draw the rooms. 1s, 2s, 2p has 3 beds. And next we're up on the 3rd floor, 3s and 3p. And let's see if that'll be enough. It is. So 1, 2, 3, 4. Here they're going to fill the bed separately first. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So again, this is all very neat and tidy, and everything's filled up and beautiful. The rooms that are filled are full. The other rooms are completely empty. And I think all of us have a little bit of understanding about, obsessive compulsive disorder, where you want things to be perfect and lined up, and you want all your ducks in a row. Unfortunately, life is not like that, and so we all have to learn to deal with that. But on some level, this makes me happy because everything's all lined up, right? It's very nice, like getting all your shoes lined up in order of increasing color or something. There's something satisfying about that. That's a long section.